Let's discuss a scalable system design of a stock exchange system like NSE, BSE or NASDAQ. We'll see how millions of orders are placed in this type of system, how we match a buy and sell orders, and then finally how the matches are executed.
So first discuss about the functional requirements. First one is placing a buy or sell order. So customer cannot directly place a buy or sell order in the stock exchange system. The order has to come via a stockbroker or stock trading app. But the stock exchange system should have the functionality, this is the main functionality, to accept buy or sell order. Next, customer will specify price and quantity of the buy or sell or stock. Support for both limit and market order. So we'll discuss more about this. So limit order is basically when customer is specifying a limit amount for the order, and market order is when the customer wants to buy or sell in the market price. System will match buy and sell order. So this is one of the main functionality of stock exchange system. So it has to match buy and sell orders. Next, order not matched can be retried for matching till end of the day or market closure time. So for stock exchange systems, there is a market start time and closure time. So it can start around 9 a.m. or it can close around 4 p.m. So like that. So order not matched, right, can be retried till the end of the day. Executing match. So this is after the match is happening, after we are matching one buy and sell order, we have to execute the match. So this here basically the payment and all are involved. Next, order expires after end of the day. So basically there is this market closure time, right? After the closure time, whatever remaining orders we have, those has to expire. Partial order matching allowed. So we can have a discussion with the interviewer whether we want to support partial order matching or not. But what is partial order matching is, so let's say someone wants to sell 10 stocks and someone wants to buy 5 stocks. So we should match this partially, right? So we can sell 5 quantity to the buyer, and remaining 5 again can be retried, and that remaining 5 stocks can be matched with some other buy order. Next, one more requirement. This is the out of scope requirement, that is listing and delisting stocks. So there will be some stock admins, they will be adding or listing or delisting stocks. Next, I am assuming few scale numbers for this system. These are not the accurate numbers. This is just for this discussion, I have assumed this number. So consider there are 100 million users and daily active users, let's say 10% of the total users, that is 10 million. Let's say we have 5,000 stock company. So also considered 500 million orders per day. So 500 million is 500 into 10 power 6 orders per day, and if we assume 10 power 5 seconds in a day, so that is we have simplified. So we have 86400 seconds in a day. I have simplified it to 10 power 5. So then we are getting 5,000 orders per second. So 5,000 orders per second, you see this is the transaction per second. The TPS is very high in this system. Now non-functional requirements. So the system should be highly available for browsing stocks. So in stock exchange system, usually customer cannot directly place the order. The order has to come via a stock trader, trading app or broker, but we can browse the stocks in this portal, so that should be highly available. Highly consistent for executing match. So when a buy order and sell order is getting matched, and when after that we are executing the match, we are processing the payments and all this should happen in a consistent way, right? So if the payment is failed, we should not actually consider that is a successful order, right? So all these things has to happen in a consistent way. Scalable to large number of users, so we have to design the system in such a way that it is scalable to any number of customers. So next we'll discuss about few major APIs in this system. So the first one is the API to place orders. So this is a post/orders API, and it will take the type of the order, whether it's a buy order or sell order, the stock ID, the quantity, and the amount. Next, we have few internal APIs. So this APIs the system uses internally. So the first one is to match the orders. So it will be a post/match API, and it will take the buy order ID and sell order ID. So here, let's say if the sell order ID is for quantity 10 and the buy order ID is for quantity 5, so only the 5 quantity only will be matched. Next, we have an API to actually executing the match. So this would be a post/execute API. It will take the buy order ID, sell order ID, the quantity. Here it will be, for this example, it will be 5. The amount to pay based on the logic we'll discuss later, and the payment information. So actually to execute the match, we need to have the payments details and all. So it will actually execute the match. So we'll soon see why we have separated these two API. So this is just to just to match the buy and sell orders, and this is to actually execute the match. Next, we have one API to view the order status. So this is a get/orders with the order ID. So it will return the status of the order. Now I have a high level design here. So this is the stock exchange system. We have stock exchange service we have. So there is this stock admin who will be able to list and delist stocks in this system, and via some trading platform, buy or sell orders will come to this service. So this is a black box. We'll try to break this into pieces, but the stock exchange service will first store the stock details in the database. So we have these stock tables here. So it will have the stock ID, the name of the stock, the status, listed at, timestamp, delisted. If it is delisted, then the timestamp of the delisting, last price we can store for the stock. So here we are just storing the last price here for simplicity. If we want to go for the event sourcing based approach where we want to store all the price changes, so we have to come up with a different database data model design, but for simplicity we are just keeping track of the last price only here. Next, the buy and sell orders are coming to the system. So we have a order request table. So it will have the order ID, the customer ID who is placing the order, the stock ID, order type, it is a buy or sell order, the quantity, the price, and status. So status can be the order can be completed, failed, partially completed, in progress. So different kinds of status for the order. And also it will have the created at timestamp. Now after the order is matched, we also will have the matched order, right? So this is this matched order table. So it is having the matched order ID, the buy order ID, and sell order ID. These two orders have been matched, and the quantity, the price, matched at, and the status, whether the matched order is executed, whether the payment is executed means the payment is successful, whether the payment has failed, whether it is an in progress status. So this is the status of the matched order for this buy order ID and sell order ID. Now next I'll quickly do some storage estimation based on the scale we have assumed. So let's say stock details is 1 kilobyte. So I have overestimated a little bit. So for 5,000 stocks, it will be 1 kilobyte into 5,000, that is just 5 megabyte. For 10,000 stocks, it will be just 10 MB. So if we are storing just the current stock price, then this will be this much. But if you want to store all the prices and for each timestamp when the stock price is changing, all the timestamp if we are storing, then the storage cost also will be much more. Next, consider 500 million orders per day, and let's consider also 100 bytes per order. So that is 500 million is 500 into 10 power 6 and 100 into 100 bytes per order. So that comes 5 into 10 power 10 bytes per day. If we consider for a year, so that is 5 into 10 power 10 into 365 bytes per year. So let's approximate this 365 to 400. So this is 5 into 10 power 10 into 400 bytes per year approximately. So this is 20 into 10 power 12 bytes, which is 20 terabyte per year. And if we are storing the data for, let's say, 5 years, then it's 20 into 5, like 100 terabytes. So this is just some rough assumptions of the storage. Now we'll dig deep into multiple sections. First, I want to discuss about the matching logic and how fairness is achieved in this matching logic. So our matching logic should be very fair. So we need to consider two things here. So first, let's say I am buying a stock at $50, and if one seller is selling at less than or equal to $50, then that is fair for a buyer, right? And if I'm selling at $50 and someone is buying at $50 or more, then that is fair for the seller. So while matching this logic, we need to keep track of these two things. Now, I have divided the black box we had here, this stock exchange service, into multiple services. So of course we are going for a microservice architecture because first for the fault tolerance, and this one service should not be a single point of failure. And next, the scale we have seen, right? The scale is huge, so we want to go for a microservice based architecture. So we are having on one order service that will be to take the buy or sell orders, one matcher service that will match the buy and sell order, and one match execution service to actually execute the match. So we have this API gateway. So that API gateway is responsible for many things like load balancing, authentication, authorization, rate limiting, API routing, etc. So the order service is taking the order request, buy or sell order request, and it will be storing the orders in this orders database. So what kind of database do we need for the orders? So let's see the order request table we had. So we are storing order ID, customer ID, stock ID, order type, quantity, price, status, and timestamps. For the so for this we don't need any highly complex schema relations and all. So we can go ahead with a NoSQL database like DynamoDB here. So later if you want to scale this database, we can partition the database using order ID. Now, like apart from storing the order request in this order database, order service will put this order request in this queue. So there will be one matcher service that will take from this, listen from this queue, and it will try to match the orders like buy order and sell orders. After that, this matcher service will store the data in this match database. Then also this matched order details also will be put into some other queue. There will be one match execution service that will listen from the this queue, and it will actually execute the matches. So match execution will have to do lots of things like first of all, it has to update the match database when the match is completed, when the match execution is completed. It also has to update the order status when the match execution is completed. And the main part of match execution is the payment. When the payment is completed, then it has to update the tables. So match execution service will talk to some other payment service which will actually execute the payment. So now this is a distributed transactions happening here. So the match execution service has to talk to this payment service, has to update this match database, order database, and all this has to happen in an atomic way. So how do we ensure this in this kind of microservice architectures? So we use patterns like saga pattern. So if we are updating the match database and then if the payment service is failing, then we have to roll back this operations we had in this match DB. Will change the status back. Also this order status will change back. Now one question comes here, like how long will wait for the payment to be completed? So let's say the match execution service has initiated the payment, but the payment service hasn't come back with a response. Let's say we are waiting for a long time, but the response hasn't come. But before that, we also have updated the match database. So how long should we wait? So there should be a timer for that, right? So that we store in this radius using some radius TTL or time to leave. We put one payload in this radius TTL, and let's say that will be active for around 15 minutes or 20 minutes. So after that, we'll see if the payment service has come back with a success before that expiry, then of course we're good, right? If before the timer expires, if the payment service has come back with a failure, then also we have to roll back the transactions we made in this databases. If the after the timer expires, then the payment fails, we are good, right? Timer has expired, then of course we have updated the rollback the transactions in this database, and the payment also failed. One problem will happen if the timer expires and after that the payment service has come back with a success response. So in that case, basically we have rolled back the the database statuses here, but then the payment is successful. So then like of course we can have a discussion with the interviewer, and we can come up with different approaches. One approach can be we can have a cron job that will figure out this kind of orders, and it will refund the amount to the customer. Next, one problem we have in this design is we cannot just have one queue. We need to have buy and sell queues separated, because matcher service has to read from these queues and try to match the buy and sell orders, right? So we'll improve this in our next design improvements. But before we go there, I want to discuss few other things. First of all, why we have introduced these queues? We want to decouple the services so that all the services can scale at their own pace. Why we have separated this matcher service and match execution service? So like matching is a very big task, and match execution service is also a big task. So that's why we have isolated and decoupled this so that they can scale at their own pace. So matcher service has to take a buy order and sell order, and based on some logic it has to match the orders, right? So and also it has some few other things we'll see later. And next it has to put it in this match database, and it will put it in this queue. Match execution service has to talk to this payment service, has to update the match database, has to update the order database. So both the services has different tasks. So that's why we have separated these two services. Now what kind of queue do you think is will be useful for our design? So once the order is matched, no other matcher consumer should consume that order, right? So once a buy or sale order has been consumed by a matcher consumer, no other consumer should read that order, because that will be already matched, right? So Amazon SQS will be a better choice for this. Next, let's quickly discuss one topic, that is the partial order matching. So we have already discussed what it is, but let's discuss it in here. So let's say we have a sell order with quantity 10 and we have a buy order with quantity 5, right? So then we can just match 5 orders, right? From this sale order we have 10 quantity, we can take 5 from here and we can match 5 orders, and the remaining 5 sale stock orders, we can add this 5 sales order to the respective sell queue. So for that we have modified our design little bit here. So earlier we had only one queue, so we have separated the queues in buy queues and sell queues, and also we have separate queue for separate stocks. So let's say this is Meta stock, Google stock, Tesla stocks. These are the buy queues for that, and these are the sell queues for that. If a sell order comes for Google, it will come here in this queue. If a buy order comes for Tesla, it will come here in this queue, right? So and it's easier for the matcher service to read from this queue, and it will try to match accordingly. So we can see that we can have separate matcher for separate stocks, or we can match it in different way. One more thing we discussed in our requirements, where if a order is not getting matched, it has to be retried again, right? So if a order is not matched, the matcher service will put the order back in the queues again. So if it is a buy order, the matcher service will put it in some respective queues. If it is a sell order, also it will put it in the respective sell queues. Now other than that, the design is same here. We see we have this matched order queue from where the match execution service is listening, and it is talking to the payment service, it is updating the database. Also we have one expired order queue. So after the market closure time, the remaining orders will be expired, right? So we can update this, we can put this orders in this expired order queues, and this orders, I have not drawn it here. We can have some workers that will read from this expired order queue, and it will update the order database that these orders have been expired. So ultimately we have the core requirements here. Now after the match execution is complete, we can put that event back into some other topic from where the notification service and analytics service can read and do their work. So every system will have some notification service, that is to notify the customers about the order status change and few other things. There will be some analytics or service that will keep track of the daily order processing, what kind of orders getting processed, the expired orders, matched orders, details and all this will be used for analytics. So this two service can read from this topic. Now one more thing I have quickly added here, we had a requirement to browse the stocks details, right? So we already have seen the stock admin will be able to list or delist stocks, and we can the stock admin also can update the price, right? So that will be stored in the stock database, and there will be some API exposed for browsing the stocks. Using that, the stocks can be browsed. So I have not gone deep into this part here, so we'll be discussing the stock trading app in our next design discussion. So there we'll be discussing about stock browsing and all. So here I have kept it very simple. Now all these services will be auto scaled, And the databases, we are mostly going for a NoSQL database like DynamoDB, so that is very scalable, and that's why like our system is highly scalable, fault tolerant. So yep. Now quickly go through the functional and non-functional requirements we have. Placing a buy or sell order, done. Customer will specify price and quantity of buy sell stock, done. Support for limit and market order. So this we have to make changes in our matcher service where based on the type of the order we have to match the buy and sell orders. So that's very doable. System will match buy and sell order, or done. The order not matched can be retried for matching till end of the day, market closure time. Okay, done. Executing the match, order expires after end of the day, and partial order matching allowed. So all this we have covered. Now in non-functional requirement, highly available for browsing stocks, highly consistent for executing match, and scalable to large number of users. So most of them we have covered. So we'll discuss about stock trading app in our next design discussion. So I think then a few more things will be very clear. So with that, I think we are done with our system design discussion here in this.